Alright, so in example number 1, we're talking about continuities, and we're going to do whether they're removable or not removable. So in this particular problem, whenever we have something like this, we said x minus 2 cannot be equal to 0 because that's what happens in a fraction. So x cannot be 2, so it's continuous everywhere except for 2. Now, at x equals 2, since nothing can cancel out because there's just a 3 in the numerator, this is going to be non-removable. For part B, we got x squared minus 1. Let's do a different problem. For this problem, in order to solve this for the 0 being on the bottom, I'm going to factor, but I'm also going to factor on top. So x plus 3, x minus 3, x minus 1, x minus 3. And so we have a discontinuity at x equals 3, and we have one at x equals 1. Now, so that means we are continuous from negative infinity to 1, from 1 to 3, and from 3 to infinity. Because the x minus 3's cancel, the x equals 3 is a removable, and the x equals 1 is non-removable. So for this piecewise function, I'm going to plug in 1. And when I plug in 1, I'm going to have the limit. This would be the limit from the right side, which we talked about later in this section. And I get 1 plus 3 equals 4. And when I plug in to the 1, which gives me numbers to the left of 1, I get the answer of negative 2. Because these two are different numbers, there's going to be a discontinuity at x equals 1. So my continuous everywhere else. If these two numbers happen to be the same, it would have been continuous everywhere. And because this is our jump, jumps are non-removable. And one more. If I did y equals the cotangent of theta, well, that's cosine over sine. So the question is, where is the sine of theta equal to 0? Well, that occurs at 0 and pi and 2 pi and so on. So we're going to go from negative pi to 0, 0 to pi, pi to 2 pi, dot, 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 all the way backwards and forwards. So because each one of these does not get canceled out, all of the discontinuities would be non-removable. Alright, for this problem, we once again need to make sure we do the 16 minus x squared has to be bigger than or equal to 0. So I need to know where 16 is bigger than x squared. Now, normally, when we solve this, we do a square root, except for we would get two answers, and you can't have plus or minus 4 is bigger than 16. So, since the answers would be negative 4 and positive 4, if I plug in negative 5, is 16 greater than or equal to negative 5 squared? And the answer is no. That will work. Then I pick a number in the middle, which is 0. Is 16 greater than 0 squared? Yes. So that basically means everything in here is going to work. And when I pick 5, I get 16 is bigger than 25, which once again does not work. So we are talking about everything from negative 4 to positive 4, and they should be in brackets because we include negative 4 and positive 4. If I wanted to determine the continuity of this, it would be a nice and simple all reals because no number is a problem in these. if I wanted to do y equals the secant of x, which is the same as 1 over cosine, I would have to talk about where the cosine of x equals 0, and that happens at pi over 2, and again at 3 pi over 2, and that way negative pi over 2, and negative 3 pi over 2, and that way, and here is where all of the discontinuities occur. Alright, one last problem for this video, and then we'll talk about the intermediate value theorem. Actually, we'll probably do this on this video as well. If I had a situation where they gave me something where they told me that the absolute value of sine of x, when sine of 1 over x if x does not equal 0, and 0 if x equals 0, I would need to find the limit as x approaches 0 of the sine of 1 over x. And if the answer turns out to be 0, then we have ourselves an answer. The unfortunate part is when we learned about this problem in 1-3, we said it did not exist because it oscillated too quickly. Now, when we want to do the same thing with the next problem where we had h of x equals x sine of 1 over x, and we have the point if x doesn't equal 0, and 0 if x equals 0, it turns out that numerically, because that's the only way we can do it, the limit as x approaches 0 of x sine of 1 over x did turn out to equal 0. So this one is continuous always, where the one up here is continuous except at x equals 0. Alright, so the intermediate value theorem says all the stuff in between works as long as we have a continuous function. So when asked if there's a root between f of negative 3 and positive 3, I plug in the numbers. And so my one answer is 4. And my other answer is also 4. And since these are both positive, the answer is simply, I don't know, because we have no idea whether it crosses 0 or not in between negative 3 and 3. If I change this to be same problem, but I said between 0 and 3, well, f of 3 is still going to be 4. F of 0 is going to be negative 5. And because we know that we have to go from 4 to negative 5, we must cross over the 0. And so that's a quick look at 1-5. The other thing that we need to check in this problem, I was going back to our example on continuity, is that we need to do our left-sided and right-sided limit. So the limit as x approaches 4 from the right of negative 4 from the right of f of x does turn out to hit 0, because what we have here is a half circle. And so since that turns out to be 0, and the limit as x approaches 4 from the left of f of x also turns out to equal 0, that means we can include these brackets. If they did not have a limit, a right-handed limit and a left-handed limit, then we would not include negative 4 and positive 4.